Hello everyone, this is Vishaal Karthik here, and in this video, we are going to see about the making of an microcontroller chip. Before starting, let's discuss what is a microcontroller. A microcontroller is a compact integrated circuit designed to govern a specific operation in an embedded system. The difference between the microprocessors and microcontrollers is just that microcontrollers perform only one action while microprocessors performs many operations. A typical microcontroller includes a processor, memory and input-output peripherals embedded on a single chip, but microprocessors don't have those inbuilt. The process 1. In this process, the sand is converted into a silicon wafer. This is the first process in the microcontroller making. The raw material chips are made of its sands. The sand look like this. This sand is made up of silicon dioxide. Silicon is the second most available element on the Earth's crust after oxygen. It only exists in bonded form. The necessary requirements for the chip is made by converting silicon into a crystalline form. The obtained final product looks like this. This is a monocrystalline of silicon rod which is of highest purity, that is, which means that percentage of impurity atom in the silicon crystalline rod is 0.0001 percentage. Now let's review about the silicon atom. The structure of the silicon atom looks like this. It has 4 outer electrons and no free charge carriers. The final pure silicon crystalline rod we obtained previously is non-conductive at room temperature. To make it conductive, we need some impure atoms built on it. So small quantities of phosphorus is built in it. Phosphorus. This element has 5 outer electrons. The fifth phosphorus electron builds into each molecule of the silicon crystal lattice can move freely. Because of the structure, the silicon phosphorus crystal is negatively charged or termed as N-conductive. Boron, on the other hand, has only 3 outer electrons. When they are built into the silicon lattice, one silicon electron will be obviously missing. This creates electron holes. They move through the crystal like positively charged electricity particles. This material is positively charged and termed as p-conductive. Transistors are the smallest control units in the microcontroller chips. Let's look at this video for a better understanding. For example, this is a NMOS transistor. In the heart of a NMOS transistor, we find out an M-conductive and P-conductive layer of silicon crystals. The additional layer covering above is made of silicon oxide and it acts as an insulator. Another layer of electrically conductive polysilicon is applied on the top of it, and every transistor has common 3 connections. Now the charges are assigned to all the connections, and obviously now the current will start flow from N-conductive to another N-conductive node through P-conductive layer. The transistor can be switched off and back and forth. This is 0 and 1. This binary system is the basic of data processing, which is the most basic thing in the microcontroller manufacturing. This is, for example, this is gigabit. 1 gigabit memory chip is of only 1.3 centimeter, but it can approximately store the contents of a 64,000 standard sized sheets of paper. Amazingly, if it were constructed using conventional components without using the transistor, it would cover the area of a small town. Process 2. How the silicon wafer is converted into fabrication. Let's see. Firstly, the layout and design are the beginning of chip manufacturing. The large number of components calls for an elaborate design process to define the circuitry functions of the chip. Because microcontroller is very small, it needs complex designing process so that all the elements can be fit inside without a space constraint. Next, the technical and physical characteristics of the chip are simulated and its functions are tested in any of the simulation software available open source or through paid versions. Up to 1 billion transistors like the one we saw before gigabit per chip are connected with the aid of wiring tools. The design tool forms a connection to three-dimensional architecture of sandwich layers. The wires are sandwiched in the board. This construction plan is transferred to mask. These are the reprographic stencils of the subsequent manufacturing process. First we draw, then we create masks of it. This is known as masking. The finished masks of the geometric image we did of the circuits that are exposed one after another in several production processes. The silicon wafers are transported from the 300 mm fabrication in a hermetically sealed containers. First, the conductive or non-conductive layers are produced by oxidation of the surface at approximately 1000 degrees Celsius in high temperature furnace. At maximum, it can go up to 1500 degrees Celsius. A drop of photoresist is uniformly distributed along all the layers by centrifugal force on the oxide layer produced, thus creating it as a light sensitive layer. Special exposure machines, so-called vapor steppers, transfers the made masks by exposure to the silicon wafer. The accuracy of adjustment to the fixtures already produced must remain with a tolerance of 1/100 of a micrometer, because these microcontrollers perform many important functions, so that the accuracy should be very precise. Next, the photoresisted coated mask wafer is exposed through a mask. The exposed sections can be developed while the unexposed feature remains still in the mask section. The oxide layer is etched off. The etching process is done through either wet etching or plasma etching. After dissolving the remaining photoresist and then cleansing, another oxidation takes place. This time, a very thin layer is affected. Electrically conductive polysilicon is deposited on this insulation layer. Then once again, photoresist mask and exposure occur, and the exposed photoresist is again dissolved. Then the polysilicon and the thin oxide layer obtained and etched off. They both remain intact only in the middle under the resist layer. The other portion was etched off. Ion implanter shoot impurity atoms into the silicon, because we already know to make it conductive we need some impure atoms built on the silicon. So we use phosphorus or any other impure atoms. This changes the conductivity of the exposed silicon by a fraction of micrometer. Structure width, distance and cover precision are constantly checked and they have been monitored throughout the process. After the residual photoresist has been removed, another oxide layer is applied. Once again, the cycle of photoresist exposure removal and dissolution takes place. Another oxide layer is applied on the top of it. Contact holes are etched in to open up access to the conductive layers, because the contacts or interconnections must now be deposited. Metal compounds are sputtered onto the water in sputtering machines. Process 3. Now the fabricated board should be converted into a microcontroller. Once again, photoresist and mask, depending on the component, over 200 meters of interconnections are created, because the interconnection portion is the most important in the microcontroller, so that we have to place all the elements without a space constraint, and they have to be wired along the board and etched off. The unexposed strips shows the path of aluminum conductor tracks that remain behind after the etching process and provide the contact to the underlying layers. The insulation layer above the interconnections must be given a smooth surface. In this production line, the individual work processes are repeated 400 to 500 times until the integrated circuit of a component is completely assembled. The 29 steps I explained will take along 400 to 500 times until the microcontroller chip of a component is completely assembled. That's it about the making of microcontroller. We have started from the silicon sand to the making of a final microcontroller chip board. Thank you very much.